A little bit about me. I've been doing.
Good luck, Jan.
I've been doing Java and Scala stuff in a distributed systems context for a while, especially with Akka, where I've also contributed a few things, especially to their HTTP layer. Recently, I've been starting to do a few small pull requests to ZIO as well, so just try the community out and see how these things go. A bit of context about today's project. I'm helping ISS, which you might know is a big services facility management company. They are revamping their global invoicing workflow and rolling out a solution of sort of one architectural blueprint of services and software that they want to use internationally. And I'm helping them develop some middleware that helps sort of tie individual pieces together. Which originally was written in Akka, and we're sort of moving towards ZIO for some parts of it. So let me introduce Akka a little bit for those of you that sort of squarely sit on the ZIO side, or maybe haven't seen either of these before. Akka is a framework that allows you to build concurrent systems using actors. The actor model you can think of as actors as individual pieces, individual processes that run independently, in case of Java, within one Java virtual machine, and they only communicate by sending asynchronous messages to each other. So they don't do method calls. You have a message, which is some sort of immutable object, and you send that to actors to make them do things. Actors themselves are very much mutable things. They thrive on having some state, but that state is encapsulated inside the actor. To affect it by sending it messages. In case of Akka, there's a class called behavior, which represents what an actor does as a result of a message, which could be changing its state, sending some other messages to actors. It could stop itself, or even change its behavior, swap out the behavior class for something else. And that is typically actually how you, these days, write actors. With Akka, you have your behavior case class encapsulate the state that you have, so that when you get a message, you emit that new behavior with the changed state inside, so that the behavior itself is immutable. And there are two other types you may come across. Actor system is sort of the root entry point to one actor that has a certain behavior, but that may have started and typically will start lots of other actors in the system that then do the actual work. And actor ref is the class that allows you to send a message to an actor. In order to do that, you need a reference to the actor. The C type you see here is the base class of the messages that an actor accepts, which are also called commands, hence the C. Then Akka, at some point when reactive streams was sort of growing as an interesting direction around 2014, I think. Akka added a layer called Akka Streams that allows you to do reactive streaming implemented by actors. The fact that it's implemented by actors you don't really see. But it was one of the earlier reactive stream implementations that actually had a very decent architecture and thought behind it. Like, we're going to go with this mental model and then build up a Scala DSL and other things around that to make that work. And some terminology there is that there are three types that are used the most, although there are other shapes as well. There's a source, which can emit elements of a type T. So we can think of that as like a little factory where once in a while an element may pop out of type T, but it's up to that source to define when that is and how fast that is. And the second type argument, the M, is what Akka calls a materialized value. That is the return type that you get when you actually instantiate the source. So the source object and the source instance is just a description of what the source will look like, a little bit like a ZIO, just it starts to run when you actually start it. But for the source, additionally to starting it, you get a result of type M. Now, if that source is, for example, represented by an actor, you could say, well, it could be an actor ref, because then once the stream starts, we can send messages to that source, and then we can affect what that stream is doing while it's running. Second important type is flow. which you can think of as something that has both an input and an output. So it accepts elements t, and then elements u come out, not necessarily one as a result of the other. It may be that it accepts two instances of t, and then one u comes out. So again, the time aspect is important, that it's a real-time can affect what these components do. Again, a flow also has a materialized value, or at least a type m, which is typically not used. And that's also actually why Akka has introduced a little weird type called not used that you tend to put into the type slot for m if you intend not to return any materialized value. That is, you could ask why it's not nothing or any. I suppose that's for Java compatibility reasons, in part at least. Then we have sync, which typically sits at the end of a flow, which only accepts elements and then either collects them into some grant result object, or maybe has a side effect of sending stuff into Kafka or into some database. And there, if you have a materialized value, you typically get a future, because that will then result with the value once the stream actually completes. Let me also introduce ZIO a little bit. I assume, though, that most of you have seen ZIO before here. You can think of ZIO as, at least the way I try to explain it to people, as sort of a fancy function that takes some input R and then asynchronously completes with either an error or a result. And just thinking of it that way makes it easy to also think of either three type parameters. They become a little less scary if you model it that way. And what makes it nice to use in Scala is that you can use the for syntax to invoke map and flat map on code that you write with that. And we're actually going to see examples where Scala syntax really helped in going from, for example, futures to ZIO, where the lines of code that you had actually didn't change much. So that's going to be quite interesting. We're going to touch, but what makes ZIO a great library is that there are a lot of interesting building blocks that you can use to build concurrent tools. Where in Akka you basically have the actor that is very powerful, but just the one concept that you build with. In ZIO, you have a lot of different smaller building blocks, like ref of t, where you can hold reference to an object and change it and read it or transform it at certain points in time. There's a queue where you can have your typical queuing behavior, add elements in one at a time, and then pull them off from the other end. You have Z managed, which is an interesting concept to wrap a resource and make sure it's cleaned up. Like if you need to launch a background task that runs for a period of time or throughout your application, putting it in a Z managed makes you aware that the task needs to stop and be cleaned up, and you also get a guarantee that it is stopped once you're done running. And with ZIO, actually, there is a reactive streams element as well. What I'm presenting here is the stuff in ZIO 1. ZIO 2 is completely changing this, and actually recently changing things even more. I'm trying to keep up, but I'm going to use the terminology here from ZIO 1, which is that you have a Z stream, which emits elements of T, a Z transducer that just emits elements, that accepts elements of T, emits U, and Z sync that accepts T. So terminology very, very much similar to Akka, but you'll see there's no materialized value here. So if you want to have some other side values that affect your stream, you're going to have to build that in some other way. Luckily, Java for a while now, I think since JDK 9 or something, comes with a standard library of definitions called reactive streams, javax.concurrent.reactive or something, that allows these different kind of reactive streaming frameworks to actually talk to each other through two concepts called a publisher and a subscriber, where a publisher is pretty much what you in these frameworks call a source or a stream, a thing that emits elements. And a subscriber is something that accepts elements, called a sink in both frameworks. And by having this, we can actually have Akka streams hooked into ZIO streams and the other way around, which is extremely useful as we are trying to make this migration as incremental as possible. Unfortunately, there's no equivalent for a flow or any other shapes that have sort of more inputs or outputs, which is not a big deal in practice because you try to have one stream be mostly Akka or mostly a ZIO either way. So what's the reason that we started to look at ZIO when we already had Akka doing a lot of the stuff that we needed? So one thing is that Akka actors these days, they are typed, so you know what commands you can send to an actor, but that can still be a little imprecise to model actual behavior of an actor. It could be that an actor accepts certain message types at a certain point in its life cycle, but not later, or maybe only during initialization. And you can't really express that because the actual type of an actor can't change. It's always the same type. And then the everything as an actor concept is true. You can model pretty much anything you want as an actor, but it might not be the most succinct way of describing things if actors is the only the pattern that you use. Like most people know what a queue and a mutable reference is, like the examples I showed in ZIO. They don't really require much explanation, yet you don't use those things directly together with actors in an Akka world, even though certain things might be easier to write down in using simpler concepts. And then unit tests always run in real time with actors. So you can obviously unit test them, but you unit test them by actually creating an actor, sending it messages and waiting what comes back. One of the cases we're going to look at is a poller that sort of every 10 seconds wakes up, checks some REST resource to see if there have been some changes. In order to unit test that, you have to actually wait some time and then check for changes, which of course you can speed up the time, but as we'll see, ZIO has some nice ways to deal with that are sort of a little bit more modern, a little bit better designed than Akka could do. Then on the Akka stream side, that little bit comes from the reactive stream specification, is that errors are typed as Java exceptions, because that's what errors look like typically in Java. I called it untyped here, which might not be entirely fair because obviously you do have an exception type, but you can't see what the type is as a stream progresses. So if you know that you're only going to get certain errors in the stream, you can't actually express that in Akka. And there was these actually things that ZIO from the get-go modeled really, really nicely. And we figured, well, that's something we want to try out. And we sort of started introducing it on some incremental things, one thing at a time, and kept pushing onwards, creeping into more and more of the code, where today most of it is ZIO. I'll give a summary at the end where we're not there yet. I should mention there's this thing called ZIO actors, which I looked at when we started this whole endeavor, but partly because it was a little young when we started this, and partly because I expected that we could model most things as something else than actors in a much simpler way. We ended up not using that. Yeah, so here's a little picture of the system we're going to be looking at. So we are writing some middleware that sits in between some invoicing software as a service resource service where we talk REST, and then downwards we have some data stores that we interact with, being Kafka, some blob storage for bigger objects, and then there is an ERP system that we also need to talk to through some other interface called OData, which is basically a layer on top of REST as well. And then there are two small use cases or small subsystems that I'll present. One is the poller that I talked about, which is a fairly simple concept that just checks a remote endpoint once in a while and then updates some stuff into Kafka as a result if there were changes. And a second case is a streaming implementation that we made for handling very big invoices. While talking to that REST service, we can typically get tens of megabytes or even more of XML, and that's just one invoice, and then there's going to be multiple ones in a REST response. And memory-wise, you wouldn't want to hold on to all of that in memory while you're playing with the XML. So we wanted to do that incrementally. Yeah, so let's look at a little bit of code. I tried to simplify this, but not clean it up too much to sort of give a honest representation of what the source code actually looks like. So this is our poller for Akka, where we have a trait called command, which is all the messages that the actor can get. You can basically see here that you can divide these up into two. There's like the public commands, which is just one called reset, because there's a public API where we can reset the state of this poller so it starts back from the beginning of time and starts to read all the invoices again. Everything else is private, so that maybe already be a smell that this yes, you can make it as an actor, but it might not be the most appropriate thing. Where there's some offset handling and other things, you see we need to have custom commands to just communicate the failure of a stream back to the actor. And as you can see, that's going to be a part of one of the ways that makes this code a bit more complex than it needs to be. Here's the class itself, which has the one public method called initial receive, and that gives you the behavior that we talked about earlier. So the information that you can use to actually start an actor that can receive commands. However, what it does first, or what it does as part of the constructor, is that we take in or create a new actor called Kafka offset, because we actually store the offset of what we're reading from the REST resource in Kafka. And we collaborate with that actor. We use that to actually store and load information. This actor doesn't do that itself. And then we send a message using ask to that actor and basically say, get us the offset. And when the message comes back, that's what ask does. When it sends a message to one actor and then expect a response back that gets sent to us as a command. In this case, it's the initial offset command that we have defined back here, which will then contain the result of trying to get the offset from Kafka, but actually as a try, because again, error handling is something that you have to do yourself. So that's all part of the command as well. Where you can say, well, hey, if we got an initial offset back, that was a success, then we're going to start polling and pull once. The pull method does a single pull. And here's some failure management that we need to do if it didn't work. And then because command is a trait with a lot of other stuff, we actually have to have a case underscore here for all sorts of other things that may happen, which actually won't happen because we haven't actually started yet. Then here's the pull function itself, which actually contains most of the only business logic that this actor is doing, which is this part here. Because the invoicing system we're talking to is called Coupa. So that's the thing you saw on the top. That's the thing that delivers invoices to us. We ask that for a stream, a Akka stream of changed invoices with some parameters. And we take that stream and send that to a flow, which is a entity producer flow in Kafka. What that does is it will take every element that's in the stream and create a Kafka message for that. And then we hook up that flow to a sink that doesn't do anything, because in this case, it's a flow that actually sends messages to Kafka. We don't have a sink that needs to do anything. So in order to have a complete stream, we still need a sink. So that's the sink.ignore. And then we run that. So that part is the only really interesting thing about this actor, where we need to take hold of a timestamp of the last seen item and use that for our next poll. So that's the code you see here. But all the rest is really just taking messages of changed timestamps, turning them into other messages and sending it back into the actor so we can keep this message loop going. Because of time, I'm going to not explain the rest and just go into the ZIO version to display that a little bit, where we've introduced a little helper class called daemon that contains a background task that actually contains the actor running, and a queue that you can use to send it commands. A little bit like an actor, if you want to talk to this poller, you can still send it commands. It's just that our command now is really just our own one object, which is reset. That's the only thing you can send us. Everything else is handled inside in this task. Cooper poller itself now just has a run method that asynchronously will yield an instance of this daemon. And that will itself sort of do everything we had in the behavior class before. So we need to get the latest offset from Kafka, but that's now no longer an actor. We just have a Kafka service where we say, get us the latest offset, and that we have here. Then we initialize our queue. We have some scheduling stuff going on, so we need a clock in our environment. We still have our pull method that sends the stream, but we simply say, well, we want to pull. but then we want to repeat that every paging delay item. So we automatically pull every 10 seconds or whatever the delay is just by telling ZIO that we want to do this every 10 seconds. And there's some sophisticated error handling, as you can see, and that becomes our background task. So just do this every 10 seconds. Pull looks still similar to what we had before, but now we need to handle the reset handling explicitly and go into the run segment method where the actual stream handling now is. Let's go into that first. So we've refactored out the actual stream handling. So here's our actual business logic, what it looks now in a Z streaming setup, where we can still get our changed entities, but now that's a Z stream. Now, because a Z stream, you can't actually send to multiple syncs without using a method called broadcast. And if you do that, you now get a Z managed instead of a Z stream. It's one of the parts of the API that were, I would say, more cumbersome to use than maybe strictly required. That's why you need to have a use method here. And now we have two aspects, which is the stream itself and the latest element that pops out of this. But now we can still use that stream inside this .use. Now use .transduce instead of .via to send that to Kafka. And again, return the latest element. So with that, let's jump to the conclusion. We've actually gotten rid of a lot of lines of code that were Akka specific and just to shoehorn the concept of polling into an actor. The error handling is a lot more visible because now our streams know what can actually fail. The Kafka part can fail with Kafka problems. The rest cannot fail. So we have our type system really helping us out on what's going on. Plus the fact that it is a poller, I only showed one, there are actually multiple ones in our system. We can now reuse the error handling and retry handling and exponential backoff and other things across all the pollers without that needing to push down into a base class. But the real difference was during testing, where ZIO's clock concept really allows you to test these kind of time-based concepts by simulating a clock and saying, well, now pretend that it's 10 seconds later, and then everything in your actor will kick off. And the really nice part is that this works not just in unit tests, it actually works in integration tests as well. So if we start up the whole application, we can still use ZIO clock to say, hey, pretend it's 10 seconds later, and then if you have the right mocks for all your dependencies, they will talk to each other, and you can run all your integration tests in hundreds of milliseconds rather than the typical, seconds or tens of seconds if you do actual network I/O and other things. We're a little short on time, so I will just present the second case here and go straight to the conclusions. So I've talked a little bit about this big HTTP response, which I tried to graph out here a little bit. So we have very, very big invoices in Coupa's custom XML format that we actually want to deal with one invoice, but one invoice line at a time. We don't even want the whole invoice in memory because that's still tens of megabytes that we don't need at once. So this graph sort of represents how we actually want the stream, the Z stream or the Akka stream to look, where the invoice content goes into invoice lines. We calculate the totals of each line by iterating through it, while we also want to transform them to the standard format for invoices that we use and store the big end result in a streaming way into our blob store, while storing a summary without the actual invoice lines into Kafka. As you may know, Kafka actually doesn't like these big objects either. So that's what we're trying to do. We initially wrote that as a Kafka streams implementation because there were a couple of things that were missing in ZIO stream. And later we returned to it and tried to implement those missing pieces ourselves, and now it's fully ZIO. Where the here. One thing that we observed was that, well, Akka, if you implement your own streaming stages, you can decide when you pull for new elements on the input and when you push elements out. And Akka will take care of making sure that whether the back pressure is downwards or upwards in your stream. But in ZIO, everything is, or was, I must say, it's least in ZIO 1, push only, meaning that it's the source that decides when something happens. That's, for these kind of systems in practice, not that much of a problem, but it did require me to sort of change my thinking a little bit. Then Akka has this nice DSL where you can say, I have this source and I want to send it to this tree, to this sink, to this sink, and to this sink. And you can express that using something that actually looks like a graph. That is much, much easier to read and reason about than having a .broadcast that gets you a Z managed of a list of other things that you have to then extract and do all sorts of other things with. So since our broadcasting was limited to having side effects, we wrote a couple of wrappers for that help out. But I can't help but think that there may be a nicer way to get that into core ZIO to allow you to write more complicated graphs than straight through processing. But the biggest limitation was actually that we needed to do something one subgraph at a time. So we have a huge incoming stream of invoices, but we want to invoke a sink on parts of that stream repeatedly. And there are a couple of things in ZIO 1 that allow you to do that. There's a zsync.push.restartable that will restart a sink when needed. And you can turn a sink into a transducer that will also start on multiple times. But they didn't have the exact things that we needed. So we actually took the code from that and turned that into something a bit more smart that allows us to take a stream and when a certain predicate is true, restart a sink that is emitting elements of a type Z, so that in the end you get a transducer that will emit multiple Z's. Every time the predicate hits, we restart the sink and we sort of start building a new invoice. Yes, so I'd like to wrap up here because of time. So for the moment, we are extremely happy with ZIO. The things we thought to get out of it, we really get. The error handling is just immensely useful, has saved us actually a couple of times on unexpected cases we didn't think about. So anybody who's using Akka right now should definitely check out ZIO and see if it sort of fits certain use cases. And in my experience, actually, the Scala language is something that's helped make this transition extremely smooth. So anywhere where there is a for comprehension based on futures, you can drop in ZIO and it will mostly work. Every time you have a stream that says sort of .filter operations, the operations are going to be pretty much the same on Z stream. So it's just fixing some compile errors, and it's you have some results quite immediately. However, there are a couple of things that could be improved, I think, on the ZIO side. Firstly, having some more basic documentation of why things have been decided to be as they are. Like the sink and transducer concepts in ZStreams 1 were never sort of described, like, why is a sink a Z managed of a push function that takes an optional thing that goes into this? There are good reasons for it that I now know after discussions and reading and other things, but that could have been written down as some design decisions. The split processing, I'm really going to keep an eye on ZIO 2 and see if I can help sort of get that fall into place, because it would really allow more complicated operations when needed. And yeah, I think I'll leave it at this. So we can take sort of maybe a 30 seconds questions if there's something from the venue or from online.
Well, firstly, thank you so much, Jan. That was amazing. Yay. And I see you're using org mode as well. I've never seen an org mode presentation.
Thank you for recognizing that. If you want to know more about how I presented, you can go back to the Emacs Conf of last week. I had a talk there on how this all works.
Oh, awesome. Okay, cool. Definitely. Yeah, org mode is beautiful. Are there any questions in the audience? I have a microphone. I could throw it. Okay, here seems good. Does anyone know if Z-channel, Vigo, will Z-channel solve the problems or allow these split stream processing? Who would know this?
Well, we need to add some operators.
We might need to add some operators, but it's great feedback as well. Yeah, thank you. Thank you so much. Last chance. Oh, yeah, of course.
To me, it seems that the only real feature in Akka that has no counterpart in ZIO or everywhere else is clustering things like sharding, cluster singleton, all that kinds of things.
Yes,
So the question is,
here
are
we
you
go.
using this one, and do you have any ideas of replacing it?
I had a paragraph here which was hidden from my view. So yes, what's keeping us from switching 100%? We're not using ZIO HTTP because they haven't modeled being able to take in an HTTP request and handling that in a streaming fashion, which technically we don't need a use case right now, but I'd really like that to be there before taking an HTTP streaming framework, right? It has to be streaming all the way. Then you mentioned the clustering. Yes, we are still using Akka, and we're gonna keep using that probably as a cluster awareness thing, because being able to have multiple copies of your service and natively knowing how many copies you have, and doing simple leader election, doing some background tasks on exactly one node, or using the cluster sharding feature of Akka, which is, if you don't know it, look into it. I did see there's a ZIO entity being presented today or tomorrow that actually, under the hood, uses that to allow you to do some ZIO-related things. But I'd very much like to see a ZIO native clustering communication thing come up at some point, so we can, have less complicated dependencies there.
Yeah, thank you.
Yeah, next functional Scala, hopefully.
Yeah.
Yeah, thanks again.
Thank you so much.
Yes, thank you guys for attention.